conference. About 25 years ago, my boss at that time took me to a meeting at the telecom company Ericsson. And there was a group of people there who showed us some quite impressive things with fault-tolerant systems. They hot-swapped code and corrected a bug while the system was actually running. One of the guys we met, he stood out to me at least. I think it was because he had written the virtual machine that this system ran on, and that it was called JAM, Joe's Abstract Machine, which I thought was kind of witty. It was a rip of WAM, the Warren Abstract Machine. And now, 25 years later, I get to meet him again. So please welcome Joe Armstrong.
I don't remember that meeting, actually. No,
I do.
Oh, that's good. Well, thank you for coming to my talk and not going to the Java talks. So I'm going to start with a question. How do we make software that runs forever and has no faults? Because that's why we're here. That's what we're programmers to do. Well, the answer is we can't. So we could modify the question. So how can we make software that runs, until the sun turns into a supernovae, or we fry the planet because global warming has run astray? And how do we reduce the number of faults to a manageable limit? Or how, perhaps we won't have no faults, but perhaps we can build systems that if there are faults, we know where the faults are. Because at the moment, we have systems that have faults in, we don't know where the faults are. I have this problem every day. I think every day when I program, I spend 30% of my time fixing stuff that's broken that shouldn't be broken. It's usually lots of things connected together, and I don't know which thing's broken. So I think we can solve that. So I'm going to talk about things like that. I'll probably get into time trouble, because this lecture started, I gave a talk in Chicago, and then this talk, then I just added some more stuff to it for another talk, and I've added some more stuff for this talk, and it's going to get unmanageable. So the guy with the 10 minutes, or right, we'll see. So programming is about connecting things together, actually. We don't write things in one language, we write them in several languages, and we connect things together. So it's really a talk about connecting things together. So let's start with the big picture. If we forget the big picture, we'll get bogged down in details. So systems are made of black boxes, and they communicate through messages, and they have state. When the system started, it's in a particular state. If we knew the state of our system when it started, that would be really good. We don't, often. When I have a fault in a program, I try to do something and it should work, it doesn't work, and I Google and say, oh, this doesn't work. And I find all these things, and it says, well, I had exactly the same fault in my system, try this. And they say something. And then in the forum that follows, people say, yeah, I tried that, and it works. Thanks, mate. Thank you, because you've saved me a lot of time. So with unbridled optimism, I try what's been done, and it fails. And then I Google again, and I find another one. And it says, yeah, I had exactly the same. And I tried, I'm an optimist, and I try this. And after 3 or 4 times, it works, maybe, if I'm lucky. Or it never works, as was the case with Grunt, which I had to uninstall because I never got it working. Why does it work for one person and not for another person? Why this person is convinced, oh, I do this stuff, it'll work. But when I do it, it doesn't work. Well, the answer is, obviously, our two systems are not in the same state when I start. They're in different states. So if I could quantify the state of a system before it started, then we could say, okay, because our machines are in the same state when we start, if we do the same things, it should work. Should, in inverted commas. I work at Ericsson, I recently got, my colleague got new MacBooks, which were delivered with the same order, same specification, and we needed the same software on them. So I thought, well, we're both going to have the same software on it, so let's do it lockstep. I'll do a few commands, and if it works, you can do the few commands. And so we've got the same software on our machines because we're doing the same project. After 20 minutes, those machines had diverged. I typed something, he typed something, it worked for me, it didn't work for him. After 20 minutes with the same machines. Isn't that horrible? That's the state that software's in today. It's a complete mess. and I'm one of the people who's made the mess, and you're the people, I'll retire soon, so you people can sort this mess out, which is, thank you very much. Okay, so systems should have some initial state. They should be made out of black boxes. The black boxes communicate, and what they communicate should be described by protocols. That's a big picture. And then we have abstraction. We should have abstraction. What's abstraction is drawing a dotted line around black boxes, and at another level of abstraction, that becomes a black box. Okay. So this is the most important principle of computer science. It's called observational equivalence. It says two black boxes are the same if I cannot distinguish their behavior by observing the pattern of messages that go in and out of them. It doesn't matter what's inside them, provided they obey protocols, then they're observationally equivalent. That is the most important principle. So there's a lot of principles of programming. That's the most important one. And it doesn't matter what's inside the black box. It doesn't matter if it's a functional language. It doesn't matter if it's Java or Erlang or C minus plus sharp squared or something. It doesn't matter in the slightest, okay, provided it obeys the protocols. Right. So systems are made of black boxes. Two systems are the same if they are observationally equivalent. Now, it's a funny thing. We can describe these protocols formally, not informally, with things I call contracts. I'm going to show you some contracts. I'll even show you how you do contracts in JavaScript. You can do static verification if you have a sufficiently advanced programming language that the protocols are obeyed. If you can't do it at compile time, you can do it at runtime dynamically. Configurations can be defined formally, and the state of the system can be reduced to a single number. So we can produce a checksum that encaptures the entire state of a system. So we know content hashes, wonderful things, SHA-1 checksums. Take your entire disk image, take the SHA-1 checksum, send it to somebody in the email, say, my system doesn't work, here's the SHA-1 checksum of the entire operating system, and they can reproduce it if they've got the same operating system. That's, virtual machines are great, right. So this talks about monads, pipes, plumbing, middlemen, all that jazz. That was actually the first slide of 3 lectures ago, so I've grafted in that's got a new beginning now. And so the important bits, I'm going to talk about composability, contract checking, black boxes, pipes, protocols, and content hashes. And if I get out of time, somebody please tell me, because sometimes I give lectures and I'm halfway through with 5 minutes to go, so it's not very good. I get off topic easily, right? Here's the title. I thought I'd started like a movie. With a movie, you go straight into the action, and then when you're 5 minutes in, they roll the credits. So I'm Joe Armstrong, and I work for Ericsson, and I'm a professor at Corte-Hall. So that's a bit of the thing. Okay, how do we connect things together? There's 2 ways. You can link them together in memory, or you can connect them with a communication channel. The first one's called shared memory concurrency. That's a bad idea. Stupid. Well, it's not a bad idea. It's okay if you want performance, and you can put them together in a shared. How do you put a shared memory for an application? The part of it's in Sweden and the other part's in America. There is no shared memory. Where do you put the memory? In the middle of the Atlantic? No, you don't. So you have to say, big systems, they have to send messages if you want this abstraction. Okay. That's how we connect things together. First one is really problematical. If you start sharing things in memory, you can corrupt memory. You need to protect the memory with locks and mutexes and synchronized methods and all that stuff. And that is painfully difficult. If you connect them through message passing channels, it's less difficult. It's not. Some new problems occur, and a lot of old problems go away. It's kind of easy to reason about, I think. We don't have shared memory. We have individual memories. I've got my memory, you've got your memory. We send messages. You might be listening, you might not. I don't know if you heard what I said, or, what's factorial for? Did you hear that? I don't know. And these messages get corrupted on the way. But we know about that. That's easy, right? Shared memory. So the only advantage is it's efficient. All the other things are disadvantages. It's got locks. There's no currency control. It's horrible. Right. Version nightmares. Oh, don't do that. Message passing. It's all beautiful. Right. Fault isolation because because you've got separated things. It scales nicely, late binding. You don't actually need to install the software until the message arrives at the machine. Provided you can get the software to the machine before the message gets there, you're okay. So it's very late binding, very nice. You can have version bliss. I'll talk about version bliss later, because I've got a way of doing version bliss. And you can have contracts. And it's actually the core of object-oriented programming. Right, so Alan Kay said about object-oriented programming, he said, the big message in object-oriented programming is message passing. It's not about classes and methods and things. Okay. So Erlang's the only object-oriented programming language on the planet because it obeys all these kind of principles. Java and things like that are not object-oriented because they do not enforce isolation. Right. Okay, so it's all about composing computations. Well, why? Because we want to make big things from small things. Okay, we've got small things, I want to build them into big things. Right. So this I'm going to have to speed up because it was how to compute 2 times x. Sine of 2 times x. It takes 36 slides to show you how to compute sine of 2 times x. It was a talk about monads. So I'm going to go halfway through and then quickly hop the last few slides, unless you really, really, really want me to tell about details of monads and stuff like that. So I'm going to compute this. Now, at first sight, that's kind of easy. Sine of 2 times x. Anybody think that's easy? Yeah. Oh, you're all dead. Right. Oh, a laughter, good. Okay. With some debugging code, that's the tricky bit. You see, it's not computing something and doing something else. It's the and doing something else that makes it tricky. Okay, so let's look at a first cast at computing sine 2 times x. Well, in Erlang, actually, sine of x is just math colon sine. It's defined in a library. Square is just x times x, and sine square of x is sine of square of x. Fine. No trouble. But we want to compose things. We want to say, okay, so what was that? There's composition. Sine of square of x, that's composing things. And so if we've got 2 functions, f and g, we say they're composable if I can compute f of g of x. And of course, different languages compose things with different syntax. Haskell just uses a composition operator. Right. Okay, so hidden state in something prevents composability. So I'll show you why that is the case. Okay, well, what's hidden state? That's something that's evil. When I first learned programming, it was a long time ago, it was Fortran, and they said side effects are the root of all evil. And what's side effects? That's stuff that's left in your program after it's returned. You call a function, and it returns a value, but it leaves stuff behind. And they told me that was called a side effect, and they told me it was the root of all evil. And then, let me see, that was in 1968 or something like that. And then Java came along and it made a religion out of hiding this stuff, instance variables and all that stuff, which really hides stuff when you call a function. It does stuff, returns a value, but it changes instance variables while it's doing so. So instead of forbidding it and making it completely illegal, they made a religion out of it, and that's where a lot of the problems come from. Now, functional programming languages don't work like that. You have to pass the state in and it comes out. So on the right-hand side here, there's a function. There's an object-oriented language. You see, stuff goes into the object, the state changes and stuff comes out. In a functional language, stuff goes in and it contains the state. Stuff comes out and there's a new state. So monads and things like that, all that they do is hide this s and s primed. That's all they do. They don't do anything else at all. Right. Okay, I said that. So object-oriented programming is the art of hiding side effects. Right. Oh, I said that. Okay. So how can we hide this? Okay, so monads. This is a quote from the Wikipedia. A monad is a structure that represents computations defined as sequences of steps. This allows... Okay, you don't want to read all that stuff, but read the red bits. Okay, the red bits say build pipelines chained together. That's what monads do. They build pipelines of things and they chain together things. So I'm just going to show you how they do that. So here's sort of Haskell written with an Erlang syntax. We've got sine and square. And then I define a function compose. Compose f of g is just a function which returns f of g of x. And then we can say sine of square 2 is just compose these 2 functions. And then we've got it. Very nice. Very pretty. Okay. But what happens if I want to write a debugging function? Suppose I want a debug sign so that it does two things. It returns a value and it has a side effect. The side effect is it prints sign's been called. And double has a side effect. It prints double's been called. Okay, so I could write a function like that. I could say that sign of, well, functional language, they can't have side effects. So the sign's been called string has to be a return argument from the function. It's not allowed to be a side effect, so it has to come out of the function. Okay, so here is a function sign with debug that returns two things. It returns the sign of the function and a string. And here's square. And it returns two things. It returns x squared and it returns square's been called. And I want that for debugging purposes. Oh, but look what happens. I can't use my compose function. If I use compose that worked before, it doesn't work anymore. Okay? I've broken composability by adding a side effect. Okay, so what you have to do is make sure that the types are conformant, that the input type of f and g is the same as the output type. Right, so hop over a few slides. Running out of time. Okay. Okay, so, yeah, we'll go to this point. Bind is an operator that takes one of these functions that's got one argument and turns it into an argument with two functions. Once you've done that, you can compose things. Right. Hooray! You've got back composability. So what this does is it takes functions A and B. It lifts them into a space where we've got these additional hidden parameters. Then you can compose them. That's going from X to Y. And once you've got a result, you can kind of decompose them to get back to where you started. That's the whole idea of a monad. And it's all about hiding stuff. Okay, that's the only thing you need to remember. Okay, people say monads are complicated. That's because they're complicated. And it's largely syntax. Actually, there's not much going on there. The idea is very simple. Right, okay. And it's like, I'm an old physicist, you know, this idea of a problem's difficult to solve in one space, so you transform it to another space, solve it in that space, and transform it back to the original space. So if you want to do, this is actually a drum, I think, where you remove something. I don't know, it looks like it's the same one. But you could take a discrete Fourier transform of that, filter it, and do the inverse transformation, and get back to where you started. Easy stuff. Meanwhile, in Erlang, well, this notation f of g of x, that's used for what I call small-step computations. But pipes and messages and processes are used for large-step computations. So, you know, parallel programming, which is very convenient in Erlang and very difficult in some languages, is largely a question of the notations and the ways you think about it. So, for example, if I say, who thinks parallel programming is difficult? Right. So who thinks sort of find starter, Earl, pipe, grep, thread, pipe, unique pipe, double? That's easy. That's a parallel program, okay? So all these bits run in parallel. Given the correct notations for concurrent things, it becomes very simple. Here we've created a pipeline of four things. And of course, find, grep, thread, unique, they all run in parallel. So it's largely a question of notation. Makes it difficult. Okay, in Erlang we don't call them pipes, we call them processes. So here's a pipeline of three things. This is again, it's, what's this do? Yeah, it's double of square. So you start off with a number, send a message to a process whose only job is to double the process. It sends it to the next guy, and he sends it to the next guy. So we create chains of parallel, and these are all run in parallel. Right, so where do we add debugging? Well, we can change what's going on in the pipeline. We can just splice it in. It all work quite nicely, so we don't need to change the original code. That's very nice. One thing about communicating components is if you want to add debugging, you've got black boxes talking to each other. You don't need to go inside the black boxes and change them. You can put something on the channel between them. And that makes it really easy to manipulate. Right. Oh, I mentioned that, observation equivalence. Okay. Remember that? Yep, okay. Functional, yep, pipes, right. Pipes. McIlroy wrote a memo to, must have been Kernighan and Ritchie, I guess, or was it Ken Thompson and Ritchie, when they were designing Unix. This is from McIlroy's notes, and he said, we should have some way of we should have some way of coupling programs like a garden hose in another screw in another segment when it becomes necessary to manage the data. in another way. So that was a basic idea in Unix. This was Kernighan and Ritchie's boss, and he said, there must be a way of connecting things together. It should be as easy as connecting a pipe together. Right. And he conceived UNIX Pipes, which allow programs to work together with no knowledge of each other. You see, they don't have any knowledge of each other. They don't know. They take inputs, they produce outputs. They don't know what's going to happen next. It's wonderful. It's beautiful. And here's Douglas McInroy, and here's Kernighan and Ritchie. Doug has been explicit in saying that he very nearly exercised managerial control to get pipes installed, which is polite talk for do it. Right. And I think this is Dennis Ritchie said, point one's garden hose connection analogy is the one that ultimately whacked us on the head to best effect. Bang. It's a good idea. Very good idea. Right. Yeah, I just some pipes. And actually, the advice to plumbers is very good, because it applies to computer scientists and computer architects. So the pipe location in your home is important for proper maintenance and water flow. Many pipes are located in walls, floors, and ceilings and are hard to locate. If you have no idea where a leak is coming from, you want to call a professional plumber who will have the equipment to locate the pipes in your walls, floors, and ceilings. So it's right, isn't it? Ethernet, where the hell do the cables go? I don't know, they're in the walls, and better call the network engineer to find out where the damn things are and how they're connected. Handyman tips. When you move into a new house or property, try to locate the main stopcock that shuts off the water supply. Do not wait until you have a major problem when it will be too late. So what happens when you get a denial of service attack? Do you know where the main water cock is to turn it off? Or does the computer department run around like, demented rabbits saying, how do you shut this thing? Oh, they're recording. How do you shut this thing off? Fit service valves on all your pipes. This will allow you to work on the bathroom sink, for instance, without affecting the water supply in the bath shower or toilet, for instance. How many of you are running sort of online banking services and things like that where you can't you haven't fitted a valve to turn a bit off so you can fix it? These are handyman tips for plumbers. Just go and look them up, okay? Because you replace the word pipe by socket or Ethernet cable, and you replace the word faucet by switch and whatever, and it's all good. And it's kind of... It's not Ericsson, actually. It's, I won't tell you who it is. I could say the company, though. No, better not. A lot of places look like this. It's not a good idea. Get your messy pipe, nice. Look at that, lovely, messy, nice pipes. I always used to use this analogy: how you Erlang, you can do software upgrade while it's running, and in fact it uses what you might call sort of replace the boiler while it's running semantics. So that's a boiler in a house. Okay, so if you want a new boiler, what do you do? Well, you would hopefully it's been done in properly. So you've got a faucet here. So maybe there's three. That one looks a good one. So you turn that one off, and maybe you turn that one off. Hopefully, that's the input. That's just the input. And if you turn the input off, the output's okay. Probably there's some other ones. You turn them off like that. You get a guy with a welding gun. He saws through the pipes. You lift out the old thing, and you put a new one in, you weld it up, and you open the valves. And that's how we do software upgrade in Erlang. It is not rocket science. It is really simple. And that's part of it. You remember the first slide said, how do you run systems forever? Well, you build mechanisms like this in at the start. Okay, you don't add them later. Not a good idea to add them later. Right. So Erlang also uses an abstraction which is called the Middleman, which I will briefly talk about. And that is, the Middleman creates this illusion that everything in the world talks Erlang terms. Okay, so if you've got something like HTTP coming into something, put a middleman there, it parses HTTP terms and turns them into Erlang terms. Now that creates the illusion that everything is Erlang. That's really good. And why is it good? Well, imagine we've got several different languages that want to talk to each other. Spanish, English, French, German, whatever. The complexity of connecting all that together is n squared. Because you've got n things that have all got to understand each other. Right. So if we put middlemen in between, we all talk Swedish, Det blir jättelätt. Eller hur? You see, we just translate English into Swedish and French into Swedish and Japanese into Swedish. That's of order n, and then we've got an order n problem in the middle, so it becomes order 2n, or it's order n. It's not order n squared, so we suddenly reduce the complexity. That's why. Why do we use JSON or XML to communicate? Because it reduces an n squared problem to an order n problem. So this is what these middlemen does. Once we've got a middleman, we can add another idea. Wait a moment. I'll go. How are we doing? Yeah, okay. So the middleman, this imposes unity on the system, where everything's different outside this world. This world here. Outside this world. This is the black box. There's a sort of inner black box. Outside this world, people are talking different languages. Inside it, they're all talking the same language. So that imposes conceptual integrity on the world. So so the middleman, it's the Higgs Boson of Erlang. It imposes order on a chaotic universe. And actually, a little plug. The Higgs Boson was discovered using an Erlang database. CouchDB, actually, which is quite nice. So I helped discover the Higgs Boson. Well, a little bit. I mean, I didn't get a Nobel Prize for discovering the Higgs Boson. Just be nice, but no, it doesn't work that way. So if we've got these things here. We've got these. Where are they? There. These Erlang terms are coming. How can we describe the interactions of those terms? Okay, so. Well, APIs. They're stupid. They don't work. Basically, because they're wrong. They're silly. Okay, so here's an API. This is not any, well, actually Erlang, but it could be any language. Here's an API for file system. Spec, that's a specification of what you can do. It says you can open a file, you give it some modes and it returns OK and a file handle, or it returns error, you couldn't open it for some reason. Or you can close a file given a file handle, and given a file handle and an integer, you can read it, you get OK, you got some data or not. So that's pretty typical of the API, the type specs you would find in C or Java, they look like that. That is useless. Okay, so why is it useless? Well, look at that program. It's well typed. Look, you could open a file and then you can close it and then you can read from it. That will go through the type system. It'll say, this is a well typed program. So isn't that wonderful? You've got a type system, it tells you what the types are. You run a well typed program, it'll still crash. So these type systems don't capture enough information to be useful. In fact, they just get in the way and they're a pain in the arse because you've got to satisfy the type system all the time. And they're totally, well, they find the odd error. I'm trying to be provocative, because I don't normally talk to Java programmers. I'm hoping you'll sort of get you riled up, but not enough that you kill me. So we'll see. Okay, so we could add some red stuff, which is this state that I talked about. Okay, so the red stuff is the same type spec as before, and now it says, okay, in the state start, we can open a file, and if we succeed in opening the file, we'll be in this state ready, and if we don't succeed in opening it, we'll be in the state closed. And when we do read, we can return OK closed. Close. If we're in the state ready, we can close it, but it would be a semantic error if we tried to. We'd get an error, but would stay closed if it was ready. And spec. Oh, that should be the ready should be in red at the top. So spec ready and read. That's OK, and you get OK some data, and you're still ready. But there's no behaviour defined if it's closed. So we could add state to type specifications, and that would actually make better programming languages. And these are called session types. If you've seen the word session type, that's all it is. So let's do session types in JavaScript. And I'm going to not apply them to the programming language. I'm going to apply them to the communication channel that's in between. And I'm going to assume it's, say, JSON or something like that going between, just to make it concrete. So here's a website login protocol. You've got a client and a server talking to each other. And I think this architecture is wrong, actually. It served its purpose. It was very good when you only had one or two things connected together. If we connect 45 things together in long pipelines with remote procedure calls between them, we really, really do want to not propagate errors through the system if they occur. You need them to stop immediately so we know where the errors are. So I'd like to put a third thing between a client and a server, which I call a contract checker. It's a contract checker which we put between the client and server. And it's a lawyer. Its job is to say if the client and server are obeying the contract. Right. And if it's obeying the contract, the message is to pass through transparently. If there's a violation of the contract, it will say, no, you are breaking the contract. Okay. So contracts are 4 tuples, state in, cross message is message out, state out. And here we are, this is a bit of JavaScript describing a finite state machine for web authentication. It says, if these are messages that you see on the channel. Okay, so if you get a message from the client, which is start, and that's what the first thing says, then you go into a state called login, and you're waiting for a challenge from the server. And then if you, in the state, wait challenge, and from the server you get a challenge, you're waiting for a response. And if you're waiting a response and you get a message from the client, which is a response, then you're waiting for authentication. That's quite easy. You can describe it that way. Or, completely equivalently, you could describe it in a message sequence diagram, where now the state that was in the finite state machine is just in red on the vertical line there. This is just a message sequence diagram. They're the same. Semantically, they contain no different information. They contain the same information, but it's just presented in a different way. Or you could present it like that. You could present it with sort of bubbles and arrows and things. So it's very much a matter of taste, I think. Some people like this, other people like... I just like text, because I find the difficult to edit. I just type the text in, it's easier. Right. Remind you what it was again. Okay, so these things here start, the black things, they're messages. So if I'm in the state start, I get a message called client. That's just the name of the message. So I need to say what parameters the message would bear. And that I do with a type specification of the message. So I can say that the message login carries a parameter called name whose value is a string. Challenge contains a random number. So that's just a JSON term, which you can serialize and send on a communication channel. And so given something like that, a message called login, that's a good instance of the login type. Okay, so the message is called login. We always require to have a descriptor that says the message called login, and it's got a parameter called name, and name's a string. So you look at, okay, so yeah, I've got something called login, and it's got to have something called name, and it's a string. So that's a valid instance of that type, and that's decidable in linear time, and it's no problem. So that's not a good message. Message login foot size 42, because that's my foot size. There's no foot size in the type specification. Doesn't say type login name string. If I said comma foot size colon 42 or foot size with integer, then it would be valid. So I can decide that. Right. So, sorry, I haven't showed you that. With those two definitions, you can very easily just write a bit of code that looks at all these messages, checks the types, and throws up its thing and says, no, this is bad. And you stop immediately. Okay. So that's how you describe contracts. Now we have to make sure that we get the right version of the contract and the right version of the software. This is called version nightmares when you get it wrong. Now, the whole industry has almost permanently got this wrong. Okay, so there are small areas where it's right. Okay, so contracts and version bliss. Okay, so this is version hell. You just have two things and you just sort of send messages. There's no version information, there's nothing in that protocol. So you're good to get. And there's a very long history of version hell. So it started with Jon Postel, and he said an implementation should be conservative in its sending behavior and liberal in its receiving behavior. And this was what I call Postel's making matters worse law. For its time, it was okay. I mean, the internet didn't have many services. So there was only one service or two services. You know which one you are. So Postel wrote the first RFC, RFC 821. if you look at all the RFCs, RFC 821 is the first internet protocol that mentions return codes. And in Appendix E of RFC 821 is the theory of reply codes. Goodness, I mean, he felt that you had to have a theory. He describes it in great detail, what reply code, 1 YZ with a positive preliminary reply. So that's where the reply code is, in HTML. Many, many years later, HTTP, the HTTP return codes are just following what Postel did in, when was that, 1982. Okay. Now, in 1982, there was this was a simple mail transfer protocol. And it was any traffic that was on port 25. It was TCP port 25. They didn't name the protocol because it was on a particular port. And that's why you have assigned port numbers. You had to go to some big committee and it said, well, we'll give you a number, and then you had to be on that port. So what happens if you want to run SMTP, Simple Mail Transfer Protocol, on port 35? Answer, you can't, because it doesn't know, and in the mail transfer protocol there is no version that says, I'm Simple Mail. Well, that was okay, because there was only one protocol. Right, but it's not okay today. Right. So I think this is RFC 821, it says something like opening and closing. At the time of the transmission is opened, there is an exchange to ensure the hosts are communicating with the hosts they think they are. The following two commands are used for opening and closing. Hello, space domain, quit, and it says hello. So that was the authentication. Everything was, if you sent HELO on port 20, you were email. Right, that's authentication, that's security, that's everything. Right, great. So here we are. Here's an example of the protocol. You open the connection and, the first one, you open it, just sends 220, and then you send hello, and it says response 250. You have to look up what those codes meant. And if you sent anything else, you got something else. Right. Now, if you look at the dates, that was 82. Right. It was realized that was a bad idea. By 2001, 82 to 2001, what's that, 19 years? Goodness, it is. 82. 19 years later. It took 19 years to get the idea that they could change the thing, and the wording changed. SMT implementation may include identification, a practice that permits more efficient isolation and repair of any problem. So it took 19 years before they thought that we should sort of make the protocol a little bit better. Wow. Well, computer science is not an area where we adopt things quickly. Church invented the lambda calculus in 1930. Java 8 adopted it last year, which only took 30, 70, 85 years before the idea was adopted. So this is pretty good. It's only 19 years. Right. Okay, so still, it's may. It's not must. Okay, so this is, so I've shown you version hell. This is version purgatory. Purgatory is one of Dante's, the different layers. You go down through the 7 layers of hell. This is somewhere in the middle. Purgatory is when you're waiting to see if you're going to go into heaven or hell. And so this is, hello, I'm version 1.1. Hello, I'm version 1.1. So that's where we are today, more or less. That's version purgatory. So I'm going to improve matters a little bit. And, by the way, it took 14 years to get version numbers into HTTP, yes. If you look at the RFCs, didn't have version number to start with. There we go. So here we are, HTTP 0.9. It's called the one-line protocol. That HTTP 0.9 was the one that sort of booted it all off. And it's described, there's a web reference there, HTTP, protocols HTTP, AS implementation.html. And what you did, notice you do telnet to port 80, that don't really change, then you get this is telnet session, you connected, and then you do get about, and notice there's no version number or anything like that. And the version, what you get back doesn't have a version number. Not a good idea. In 1996, let's have a look, what was that? I haven't got the date on that one. The version of the HTTP message is indicated by an HTTP version field in the first line of the message. If the protocol is not, we must assume that it's in 0.9 format. So now we've got version numbers in. It took a long time, but Okay, it's a good idea. Right. So it took 14 years, thank you, to get to the idea that having a version number might be a good idea. So let's do a sort of quantum leap to a slightly better world. This is what I call version bliss. Okay, so just to remind you what content hashes are. These are things like SHA-1 checksums, MD5 checksums. They take a blob and they compute a number from it. And two blobs are the same if they've got the same number. Okay? So a file can have a content hash. A directory can have a content hash. How do we do that? We take all the files in the directory, list them with their content hashes, put them in a text file and take the content hash of that. That's the content hash of the directory. And therefore, an entire operating system has a content hash. So we can reduce an entire operating system to a single SHA-1 checksum, which is a 120-bit number. And that completely describes the operating system. Okay. So we can describe a protocol by a content hash. And we can do two things. We can either take the specification, the text file that had the specification, we can compute the content hash of that. Or we could take the software that the server has and we could use the content hash of that. And we could put that into the message. So if we took the software itself, computed its content hash, and then put that in the header, so it's the first message, then you would be guaranteed that the software that processed it was the software that you had intended it to be, and nothing else. So you wouldn't be able to get out of that one. And data protected by content hashes is immune to man-in-the-middle attacks. And if I know the content hash of something, I say, okay, I've got this content hash in my hand, go get me this blob. You get the blob, you compute the content hash, it's the same as the blob. Then a man-in-the-middle cannot have changed that. So it's an intrinsically secure procedure that doesn't require secure sockets or it doesn't require any cryptography. It's really rather nice. And of course, we're all used to content hashes. We're all functional programmers today. Anybody use Git? Right. So Git's a purely functional programming language, okay? Because it's got non-mutable state. That's why Git data stores are cacheable. That's why it works. The reason Git works is because of immutable data stores. So you're all using functional programming. It's just you don't know you're using it. Right. Okay, so here's version heaven. You send in the protocol the content hash of the software that's receiving the message or the content hash of the protocol or something like that. You make your mind up about that. And then everything's going to work fine because you're not going to get version nightmares. Right. Okay, so here's contract heaven. You've got that. You put a contract checker in the middle, and you check all these hashes to make sure they're right. And then nothing's going to get through that's not accepted by the contract checker. And you can stop things immediately when they go wrong. I hope. Right, so back to the big picture. Here's the big picture, which I started off in the first slide. We've got state, the system. We can describe state with a single content hash of the entire system. We can describe the protocols by a single content hash of the protocol. We can put contract checkers between things, and then when we connect our black boxes together, we will know that they are behaving according to the specification. Well, that's not quite true. What we'll say about errors is that components that are connected together will exactly follow a protocol, or they will fail. And that will make it much easier to build complex systems. Well, I finished early. Goodness. Sorry. Yeah. Oh, that's great. So I've got 5 minutes for questions, or you can just go off and get a cup of coffee or something. I don't know. Any questions? Yes.
Can you use that kind of hashing with any backwards protocols where you don't need to update both ends at the same time?
Well, you probably need a kind of negotiation then, I imagine. I mean, I see a lot of, you say, hello, I speak these. And if it's one of those, yeah, but then you could impose that, and then you could say, well, yeah, the old ones which don't. Well, it's like in the HTTP one. It said if you don't have a version number, we'll assume it's 0.9. Presumably, you could say if it hasn't got a content hash, we'll assume it's version 2.6 or something like that. So yes, I guess you could.
So they need to be an ordered list of.
Yes, I think so. Yes. And I think you'd like to migrate systems from being big monolithic things to lots of small things connected together, which of course increases the scalability and the fault tolerance of the system. So more questions? Don't be shy. Okay, is that?
Okay.
Okay, thank you very much. Thank you. Thank you. I finished early.